It's my pleasure today to talk about my work towards knowledge-grounded text agents. I'm going to start the talk by sort of giving an overview of text-based games and some of the baseline agents. Let's see if the slides work. Okay, perfect. So text-based games, such as the well-known Zork, are interactive simulations in which the state of the game is described entirely in text. Actions, shown here in green, are also entirely in text. And there are various types of actions, but most involve interacting with some of the objects in the surrounding environment, like the mailbox in this case, or navigating to a new location, as we can see from the Go North action. The environment keeps track of the game score, which is typically correlated with the player's progress through the storyline. And for the purposes of training reinforcement learning agents, we will typically use changes in game score as a reward for the agent. Throughout this talk, I'll be mentioning the performance of text-based learning agents. And performance is typically quantified by the percentage of possible game score that an agent can collect in a particular game across a variety of different games. So we created a framework called Jericho that's an open source evaluation framework focused on man-made text-based games. The goal of Jericho is to really help the community understand the landscape of text-based games and to be able to perform comparable and reproducible research towards reinforcement learning agents with language understanding capabilities. As a part of this, we've broken down the supported games in Jericho into different sets, which have easy, medium, and hard difficulty categories, and quantified some of the challenges that these types of games present. So if I'm going to zoom into this table, we can see some of the challenges are the size of the action space faced by the agents, the length of the game in terms of the number of steps that a walkthrough would need to take in order to solve the game, the reward sparsity, quantified in terms of the average number of steps between the game giving the agent rewards, and a number of other factors that can make games tricky, such as the stochasticity in their transition, the presence or absence of dialogue between NPCs, darkness, which will often require the player to find some source of light to continue exploring, non-standard actions, and inventory limits. So one of the first challenges that's faced by a text-based agent is the combinatorial action space presented by these games. Really, at every step of the game, the agent needs to generate a language-based action. And in the naive case, this could take the form of having a search through the space of possible actions, where the space of possible actions is defined by the vocabulary that the game's parser accepts. The added difficulty to this is that while there are really hundreds of millions of possible searches through this space of words, there's only a few actions that are going to be valid. And by valid, I mean the action is both grammatical and contextually relevant. So for example, this action on the left, take coins from man, is likely a valid action because it's grammatical, and if there is a man at the current location that has coins, then it would probably work in terms of doing something in the game. The action on the right, show my until Cyclops, is neither grammatical or contextually relevant. So this would be an invalid action in the sense that it would not be recognized by the game's parser and would not change the game state. So really the trick is, out of the millions of possible actions, being able to find and identify the set of tens of valid ones. So as you can imagine, for reinforcement learning agents, it's very difficult to be able to naively search through this language space. So in the next couple of slides, I'm going to present two agent archetypes that really help us begin to process this challenge of the action space. The first of the archetypes is what I'll call template decoding agents. And these agents, such as the TDQN agent, rely on templates that are provided by the Jericho engine through decompiling the game's language parser. The templates, which we can see on the left, take the form of a fill-in-the-blank style, where the agent can select one of the templates, like take blank from blank, and then pair that with the number of objects in the game's vocabulary to come up with an action, such as take lantern from case. Now, the TDQN agent that we can see on the right is attempting to estimate Q-value distributions over the templates and the objects to fill those templates with. For the state of the agent, TDQN uses recurrent neural networks such as GRUs to encode token by token the text of the narrative, the text of the contents of the inventory, the text of the location description, and the text of the previous action that the agent took. All of those representations are concatenated into a vector representation of the agent's current state and passed through some nonlinearities in order to estimate the Q values of what action should be taken in the current state. TDQN is trained using the standard DQN style training with a temporal difference loss and a replay buffer over past experiences. The second archetype of agents are valid action agents, such as the DRRN agent shown here. Now, these agents rely on a list of pre-identified valid or admissible actions for the current state. And these actions can be acquired through Jericho by using the handicap to ask for the actions for the current state. So as you can see, you get the observation of being in a living room, and the Jericho simulator can tell you the list of valid actions that you can actually do at the current state you're in. Now, this agent is very similar to the last, with the main difference being that it encodes each of these valid actions separately as a part of the representation, and then simply outputs a Q value that quantifies the expected amount of reward for taking that action from this current state. So typically, when we have a variable number of admissible actions, they will each just be encoded separately, and we can get a distribution of Q values that can then be sampled from. The previous observations of narrative, inventory, and description are also encoded similarly with the TDQN agent. And likewise, the training of DRRN also uses the temporal difference loss and the replay buffer. Okay, so just to wrap up this introduction, we typically evaluate these agents by comparing the average game scores in the final 100 episodes of training the agent across a variety of games. Sometimes the agents are also evaluated using a normalized score, which averages, which says on average what is the percentage of maximum possible game score the agent is able to collect, averaged across the set of games that they're evaluated on. So for example, we can see that the DRRN agent receives an average normalized game score of about 10%, showing that on average across the games that it plays, it receives 10% of the maximum rewards, while the TDQN agent receives about only 6% of those rewards, and a random action agent receives less than 2%. In general, these numbers make sense because DRRN benefits from the strongest version of the handicap by having the valid actions pre-identified for it. All right, so the main topics that I wanted to talk about today for text-based agents are knowledge representation, affordance detection, common sense reasoning, and language grounding. And I'll first start by talking about knowledge representation, or how an agent should represent the information collected through the course of its interactions with a particular game. Now, why is it important to represent knowledge? Well, text-based games are often having tens to hundreds of unique locations featuring different objects and puzzles. However, the agent's current observation only describes the current location the player is at, and it's common that human players will create detailed maps to remember where they've been and how to return to previous points of interest. This is one of the maps that someone has created for the game of Zork. And as you can see, there's quite a number of different rooms with different objects at each of the rooms. So knowledge graphs provide a really appealing way for the agent to represent its understanding of the simulated world state. They organize information into graphs that are composed of locations, objects, and attributes of objects, as well as the relationships between these. In the Zork example on the left, we can see an idealized knowledge graph representing the concepts of ownership, which you can see in the you have egg relation here. Location, such as you in behind house, which is a sort of way of saying that you're at the location of behind house. Connectivity, where south of house is south of behind house, so that's sort of representing the style of a map. And object affordances, such as the window object has the affordance openable. So two key questions involving knowledge graphs are: first, how do we construct accurate knowledge graphs that contain relevant information to the agent? And second, how do we effectively use the information stored in the knowledge graph to improve the agent's performance? In the next few slides, I'm going to go over some of the approaches that we've taken to answer these questions. So early attempts to create knowledge graphs relied on heuristic-based parsing of observation text in order to extract subject relation object triples. So for example, the agent would see the text in the corner of the house. There is a small window, and ideally we'd want it to extract the triple house has window and add that triple to our knowledge graph. Subsequently, this knowledge graph could be useful to the agent in a couple of different ways. So this is a diagram of a template decoder agent known as KG-A2C. And as we can see, it features a lot of the same components as the previous template decoder architecture. It's still using GRUs to encode room descriptions, inventory, previous actions. So all that is the same, but now we're also adding a knowledge graph into the mix. And the knowledge graph is updated using these heuristic rules like I described. But moreover, it's also being used by the agent to create a graph embedding, which is then fed to a multi-headed attention, and that becomes part of the agent's state representation. So the second way, though, that we also found that knowledge graphs can help is by using them to create masks over the objects that should be decoded. And the intuition behind this is that we really want to constrain the space of objects that the agent can use for creating actions to only feature those objects that are present at the current location. So what we can do is we can use our knowledge graph to generate an object mask that's going to disallow us from decoding any objects that are absent from the agent's current location. And that can help sort of in terms of speeding up the agent's ability to quickly explore the space of relevant actions. So this is an ablation experiment that we ran on Zork using this type of a knowledge graph-based agent. We can see that several lines, the baseline A2C agent does not have the benefit of the knowledge graph, and that's the lowest curve here. Whereas the knowledge graph-based agents, whether they're using the full model, which is using the knowledge graph for both masking actions as well as the graph attention, as well as the agents that are just using one of those two modalities of functioning, typically perform a bit faster in terms of reaching the asymptotic performance compared to the agent that has no access to a knowledge graph. So we concluded that having either graph attention or the graph masking leads to slightly improved learning rates as opposed to having no access to a knowledge graph. However, this has been one of the challenges of working on these knowledge graph approaches is, as we can see, there's no real change in the asymptotic game score. And that leaves some open questions as to whether for the current generation of agents, the knowledge representation is really the bottleneck in terms of agents' performance, or if there are other aspects like exploration that are holding back the agents. So a more recent study, a more recent strategy for creating these knowledge graphs, which is being explored by Prithviraj Amanabrolu, disposes of the rule-based heuristics in favor of using a question answering system to try to construct the knowledge graph. So in particular, this Albert QA system can pose targeted questions, such as where am I located? What objects are here? What do I have? And use the answers from those questions to construct the meat of this knowledge graph. But the question is, how exactly is this QA system being trained? So it starts by extracting a Jericho data set that consists of game locations. So for the game reverb, one example location is behind the counter of Mr. Tasty's Pizza Parlor. And you can see some objects and observations. And what this data set consists of really is questions about, where am I located, what objects are here, as well as ground truth answers that are determined by introspecting into the emulator. And by training on this set of questions and answers, it's possible to pre-train a QA model to be a little bit more flexible than the heuristic-based knowledge graph extraction style of model. So by performing this type of data set training across a large number of games, then the QA model can get increasingly general in its ability to identify the attributes of different types of objects, like a note is likely to be readable, and as well as being able to identify the names of locations and the names of the objects that are present. So this is ongoing work, so it's a little bit early to have results on this kind of knowledge graph creation, but I'm excited to see where this style of knowledge graph will go. And one more style of knowledge graph, which was explored by my colleagues at Microsoft Research, uses a continuous representation tensor to encode the knowledge rather than having the discrete triples that were previously described. So what we can see here in this picture, which I know is not very readable, is an adjacency matrix for the is relation. And we can interpret this by zooming in. And we can see that the yellow potato can be interpreted as fried and sliced through this graph representation. So on the X and Y axes, we have the list of objects that the agent might encounter in the game, as well as some of the statuses like fried or sliced that those objects can take. And all of these indices into this matrix tell us the status of the current objects for the relation is. Now, typically what we'll want is to have a set of relations. And if we think about having this equivalent matrix for each of these relations, then we have really an adjacency tensor that's representing the agent's world state. One note is that it is necessary to sort of predefine the number and the types of relations, as well as the list of possible objects and attributes that we see on the X and Y axes. So how are these adjacency tensors actually learned? Well, the graph-aided transformer agent, also known as GATA, learns a graph updater component that generates updates to the current knowledge graph based on the RNN state, the previous action, and the current observation. The updated graph is then fed into an action selector network, which follows the valid action agent archetype, and similarly encodes the knowledge graph using a graph encoder as a part of the agent state. It then attempts to score each of the possible valid actions and select which action is most promising. But going back to the graph updater, there's a couple ways that this graph updater is pre-trained in order to make good knowledge graphs. The first way is through contrastive learning, in which the agent is trained to differentiate between observations that are coming from the true current state versus observations coming from fake states. And the second way is through observation generation, in which this graph updater is trained in order to reconstruct the text of the observation token by token using only the current knowledge graph. So this is an example of the observation generation task. At the top here, we can see the ground truth text of the agent's observation. And at the bottom, we can see the predictions, the predicted text that is decoded from having only access to the knowledge graph. And what you can see is there's actually quite a bit of overlap between the types of objects like the kitchen, the fridge, the raw chicken leg, the oven, the table, that are being featured both in the original text as well as the decoded text. And in fact, the decoded text often just leaves out a lot of the flavor text in this environment and just sort of cuts to the chase by only describing the minimum amount of information. So it's actually difficult though, when it comes time to visualize and try and understand the representations that are used inside of this continuous knowledge graph. So this is again the adjacency matrix for the is relationship for after the graph updater is pre-trained using the contrastive observation classification task. And as we can see, activations are from -1 to +1, but it's just very hard to interpret how this knowledge is being used by the agent. Similarly, a learned belief graph after training with the observation generation task is quite a bit sparser, but also more difficult to interpret. However, we can still quantify whether these graphs help in terms of the performance of the downstream text-based game agents. So one encouraging thing is that if you have access to the ground truth graph, here in blue, the GATA GTF, this agent is making very significant improvements over the baseline non-knowledge graph-based agents in all of the settings that were explored. The approaches to learning the knowledge graph through generating observations and contrastive learning, as well as a combination of those, are generating more modest improvements over the baseline, but are still doing better than not having access to knowledge graphs at all. So in the future, I think it would be interesting to see if knowledge graphs can continue to improve in terms of their accuracy, as well as their flexibility for dynamically being able to handle new types of relations and new types of objects in a game. So in the next portion of the talk, I'd like to focus a little bit more on the affordance detection and common sense reasoning components. Broadly, I like to think of affordance detection as the ability to find reasonable ways of interacting with an object. For example, when you come across the mailbox in Zork, it's common sense for us to know how to open it, remove any contents, and expect to be able to read the contents that you remove. But as humans, we really benefit from the years of embodied experience with these objects in order to develop a set of sophisticated priors that we can bring to bear on new objects that we find in text games. So in this section, I'll be talking about some ways in which we've tried to imbue text game agents with similar priors. First, though, a good question is, why do we need to learn priors if we can just rely on Jericho to extract the valid actions for the current state? So a recent study has actually shown the drawbacks of relying too heavily on this valid action handicap. This study really aimed to understand what degree valid action agents were making use of the semantic meanings of the text that they were presented, both in terms of the observations and in terms of the valid actions. To do this, the study looked at two different ways of ablating the agent's state observation and action space. So here in this box, we see the normal state observation for the game of Zork, as well as the text, the normal action text. The first way of ablation that we explored was called min-ob, which would replace the observation of the current location with just the name of the location, but remove all the descriptions of the objects that are inside of it. Actions remain the same under this representation. And the second way, which is a little bit more extreme, was to hash the text of the observation, as well as hash the text of each of the valid actions. So this hash representation is entirely devoid of semantic meaning, but it's consistent in the sense that if you return to the same state, the same location, then you'll get the same hash of that location. So we trained this DRRN, the valid action agent, using these 3 different representations. And as we can see from the normalized scores across a variety of games, the DRRN hash is performing higher than the DRRN base agent, which has access to the full text of the observation screens. The DRRN with just the location names actually performs somewhat lower than the others. So this result actually highlights the fact that the valid action handicap might be a little bit too generous for training these text-based agents, particularly if we want them to emphasize learning semantic information from language. So motivated by these results, we were interested in trying to bypass the need for this valid action handicap. So in work with collaboration with Karthik Narasimhan and Shunyu Yao, we explored the idea of trying to train a model to be able to generate candidate actions for arbitrary states. The simplest form of this model would simply map the current observation into a set of actions that are likely to be valid. And in order to do well across a variety of games, it's reasonable to expect that this model would need to have a pretty good understanding of object affordances, as well as common text-based game interactions. So we referred to this model as the Contextual Action Language Model, or CALM, and it's based on the idea of trying to fine-tune a pre-trained GPT model for the domain of text-based games. A little bit more specifically, we trained this CALM model using a data set of human gameplay trajectories of the form of observations and actions. And particularly, the model is trained with a context that consisted of the current observation, the previous observation, and the previous action. And its job is to try to predict the action taken in the data set at the current time step. We trained 2 models, a GPT-2 model, like I mentioned before, as well as an n-gram baseline model. And while the GPT-2 model has a lot of parameters and can really flexibly model the complex dependencies between the context and the actions, the n-gram model really only calculates the action probability based on the n-gram statistics of actions. But in order to keep it a little bit more relevant to the current context, we allow it to generate only actions that are paired with objects that are seen in the current observation. So in order to get training data, we collected human gameplay transcripts from a website called Club Floyd, where players would gather weekly to jointly solve a text-based game. So this website's been around since 2007, and since then, over 590 different games have been played by the people with a really diverse set of game types and game genres. It's worth noting that these human actions are somewhat noisy and are not always optimal in terms of going straight for the solution of the game, but they do have a great amount of text game common sense. And in order to evaluate the quality of these trained models, we used 28 games from the Jericho benchmark, where we have access to the game simulator files, the admissible actions at every step, as well as optimal walkthrough trajectories that have been annotated to solve each game. And importantly, there is no overlapping games between the Club Floyd dataset and the Jericho evaluation benchmark. So just to get a sense of qualitatively how these models perform, we can compare some of the actions generated by each of the different models for the observation, again, from Jericho being in the living room. The n-gram model, as we can see, generates some pretty reasonable looking action completions for the current state involving, interacting with the door in completely reasonable ways. The GPT-2 model can also generate quite good completions, quite good actions. And moreover, it is able to generate the correct action that was found in the walkthrough, the action of moving the rug. So to get a little bit more quantitative with the evaluation, we evaluated Calm's performance by comparing the generated actions to the ground truth valid actions across a wide variety of states taken from walkthroughs of Jericho games. And for each of these states, we wanted to quantify the precision and recall with respect to the ground truth valid actions. And each of these graphs below show the performance as a function of the top K actions that are decoded from the model. On the left here, we're interested in the recall of the gold action, where the gold action is defined as the action that's taken by the walkthrough. And we can see that GPT in the orange actually gains a significant amount of performance increase over the baseline n-gram model, especially as the number of actions increases. And that's also true when we're trying to quantify recall over the full set of valid actions. So this sort of indicates that GPT has a little bit more diversity and can capture some of these uncommon and complex actions that the n-gram model struggles to capture. However, we can also see that the precision has somewhat of a trade-off, because as we quantify the precision of the generated actions with regard to this full set of valid actions, as we can see, as the number of actions increases, the precision tends to drop off for both of the models. So these results sort of give us confidence that across a diverse set of states, GPT can be fine-tuned to generate relevant actions. Okay, so we then wanted to integrate this pre-trained Calm model directly with the valid action agent DRRN. And this was actually very simple. What we more or less did is we dropped it in as a replacement for the valid actions that were generated by Jericho. So this model is simply given the previous observation, the current observation, and the last action, and generates a set of what GPT thinks are the best action completions, the best valid actions. We heuristically choose the size of that set to be 30, and those action candidates are then fed into the DRRN agent in replace of replacing the ground truth valid actions. It's also worth noting that the DRRN agent is trained to maximize game score as before, simply using the predicted actions now instead of the ground truth ones, but we are freezing the weights of this Calm model during reinforcement learning training so that its weights stay frozen. So how do the Calm generated actions do when they're used by DRRN? It's actually the case that they do not so badly. As we can see across a set of games on the left, Calm is getting about 10% of the possible score, whereas the n-gram version of Calm only is able to collect about 5% of game score. Comparing to KGA2C and the DRRN agents, which do benefit from the ground truth valid action handicap, we see that we can't actually match the same performance as DRRN, which might be reasonably expected. However, there are some interesting cases where in 8 of the 28 games, the Calm model actually did outperform the DRRN model, which has access to the ground truth actions. So that was a pretty interesting result to us. And I think one of the possible explanations is that the Calm model might be better focusing at the most relevant actions and helping the agent to speed up its exploration process. Okay, the final topic I wanted to talk about is language grounding. Text games offer limited ability to ground the objects in their affordances and the actions in their effects, but they lack the stronger sense of trying to tie abstract language concepts to physically realizable entities. For this reason, I'll briefly outline our recent work on grounding language in an embodied setting. And When we began this work, we were motivated by the idea that abstract language can be used to clearly express common sense rules and preconditions about objects. So if we consider the example of a household robot who is tasked with preparing a bowl of cereal, abstractly that we know that it's necessary to find a spoon, and also that spoons are probably located in cabinet drawers, and that objects such as spoons can be cleaned in the sink. So in other words, the question that we were wondering is whether it's possible to learn abstract priors and affordances in a text-based environment, and then use these priors that we've learned to help us generalize inside of a physically embodied environment. To explore this idea in joint work with Mohit Sridhar and my colleagues from MSR Montreal, we combined the Alfred embodied simulator with TextWorld, which is a game synthesis engine. This combination was dubbed ALFWorld and features, it's an environment that features over 3,000 aligned text and embodied tasks. As we can see on the right, the same underlying task can either be rendered into a text-based game through the TextWorld engine or a visual representation via the Alfred engine. Actions in TextWorld, such as the go-to cabinet action, are abstract and high level and correspond often to a sequence of actions, of low-level actions inside of the Alfred engine. So for example, to go to the cabinet, the embodied agent might need to rotate and move forward and look up or down. In contrast to other works on language grounding, ALFWorld is fully interactive, both on the language side and on the embodied side. And we believe that gives us a sort of unique opportunity to sort of deeply explore the equivalence between textual actions and concepts and their embodied realizations. The environment is open sourced at the link above. Of late, there's been a lot of work and interest in these types of environments, like room-to-room navigation or embodied question answering. But typically, these environments have only been interactive in one modality. So for example, in room-to-room navigation, the language is used as a way to specify the task, but the language itself is not interactive. The interaction only happens inside of the embodied modality. Okay, so this is a video of an example ALFWorld task. I'm going to hope the video plays okay on through Zoom, but let me know. Let's see. Here we go. So in this video, we see an agent that's tasked with trying to heat a mug and put it into the coffee machine. So first, the agent needs to search the kitchen to find the mug. It first searches the cabinet, but is unable to find the mug there. So the next place it decides to go is, as we'll see, the kitchen countertop to look for the mug. Once it reaches the countertop, it is able to successfully find the mug. Now, holding the mug, the agent needs to heat it in the microwave. So it opens a microwave and heats the mug. Then in order to complete the task, it now needs to place the mug into the coffee machine. So it first goes to the coffee machine and then puts the mug down, completing the task. And while the task of sort of microwaving an empty mug doesn't make too much sense, it is within the range of possible things that a kid might attempt inside of a kitchen. Hopefully the video was viewable on your end. Okay, awesome. So we created a modular agent that we called Butler, which uses a text agent to try to generate high-level action sequences, such as take plate from dining table, that are then translated into low-level embodied actions via another component called the body or the controller. And finally, for the embodied modality, we have a third component called the state estimator, which takes the visual images of the current embodied location and attempts to convert them into textual representations that can be fed back into the text agent. I'm going to overview some of the results that we had. There's a lot that I will not have time to talk about with regard to this agent, but the main high level is that we first pre-trained the text agent inside of the text world only environments. And this was actually done via supervised learning. We found it very hard to have reinforcement learning work in this setting. So on these text world environments, the numbers in this graph or the table show the success percentages of different tasks for seen and unseen room configurations. As we can see, the text world agent is able to solve, more than half of the instances in each case. And then what we're interested in doing is seeing whether these priors that the text agent has learned inside of the text-only environment can then generalize into the embodied environment. So in this Butler column, we then take our pre-trained text agent and attach it to the controller body and the vision state estimator and place it into the embodied setting. In this case, we're trying to evaluate the zero-shot generalization capabilities of how well this system would work. And as we can see, the success percentages drop by about 50% compared to the text-only part. And one of the reasons for this loss in performance is actually some of the discrepancies between the abstract text environment and the embodied physical environment. So for example, the abstract text environment has very little notion of physical constraints. So for example, you could potentially put a watermelon inside of a cup, inside of the abstract environment. But if you tried to do that inside of the physical environment, that wouldn't be feasible. So these types of discrepancies can generate some disconnects and a bit of a domain gap that the agent needs to overcome. We finally also tried to evaluate the performance of this agent on the setting of having goals that are generated not from templates, but by human annotators. So in particular, you can see some of the example types of tasks that human annotators have asked the agent to do. And as one might expect, the language is a bit more diverse and natural than what we would see inside of the template-based tasks. So the performance that we see, again, drops with regard to the previous baseline, but still actually we're happy to see that in a lot of cases it's getting non-trivial amounts of performance even for these human-generated tasks. So in general, our results show that it was possible to learn pretty good abstractions about how to abstractly, interact with the world using text only, and then subsequently take these priors that we've learned and help them help agents generalize into diverse embodied settings. All right, so I'll wrap up here. In my opinion, is a really challenging and rewarding domain for learning-based agents. We've barely scratched the surface on the path towards addressing many of the fundamental challenges of knowledge representation, affordance detection, common sense reasoning, and language grounding. I wanted to say a big thanks to my collaborators, without whom this work would not be possible. And also thanks to Robert and the UCL Dark Lab for inviting me. And with that, I'm happy to take questions.